Jean-Claude Cuenin from Loughborough, and he will tell us about spectral cluster bounds for orthonormal functions.
Thank you very much for the introduction, and thanks to the organizers for the invitation. So the talk today is related to yesterday's talk of Xiaoxi, so sorry for the pronunciation. So this is about LP bounds for eigenfunctions or spectral clusters, but the difference in my talk is that we will be concerned not with a single function, but with a system of functions, system of orthonormal functions. And this is joint work with Yi Nguyen, who's now in Lille, and with Xiaoyan Su, who's my postdoc in Loughborough. Okay, the plan is the following. So first I will give an introduction, some motivation why this problem is interesting and where it comes from, and maybe discuss some potential applications, although the focus of this talk is not on application. I will speak about some applications to spectral theory later, and then I want to focus on the second part, which is spectral cluster bound for rough metrics. So metrics that are just C2 or Lipschitz, for example. And then in the third part, I will talk about spectral cluster bounds on manifolds with boundary. So the first part is without boundary, and then the second part with boundary. So here's some motivation. Maybe some of you know the Lieb-Thirring inequality. So let's start with something simpler. Probably everybody knows Sobolev interpolation inequality. So this is maybe not the usual Sobolev inequality that you're used to, but you see normalizer function in L2, so these have different homogeneity, so it's called the Sobolev interpolation inequality. And what it tells you is it's kind of a form of the uncertainty principle. If you know that your function, so your function is L2 normalized, and the gradient, so this is bounded here, this is bounded by some constant, so the function has basically bounded frequency, then it cannot concentrate too much in at the point, right? It has to be in some LP space with p bigger than 2. So it has to kind of use up space and cannot concentrate in position and frequency at the same time. And then there is an upgrade of this inequality. So if you take n equal to 1, you recover exactly this inequality here. But the upshot of this inequality is that here we are assuming that the functions are not just normalized in L2, but they're actually orthogonal to each other. And so what you gain here is that you can improve the bound that you would get by just using the naive triangle inequality. You can improve the dependence on the number of functions. Namely, you see that here you have a constant which is independent of n, and if you had just used the triangle inequality, and for example, if you take all the functions to be the same, so they're not orthogonal, then you would get a dependence on n with some positive power. And this was crucial in the application of Lieb and Thirring. So they used this inequality to give a simpler proof of the stability of matter in quantum mechanics. Okay, so this is called the Lieb-Thirring inequality. There is a whole zoo of things that are called Lieb-Thirring inequalities, and I will talk a little bit about them, but this is not the focus of the talk. So maybe what we can learn from this is that this kind of abstract orthogonality that we impose here actually manifests in a very concrete and structured way. Namely, the functions have to go out of each other's way, right, to make a certain LP norm smaller than what you would get by just piling every function on top of each other. So in other words, some people like to say that orthogonality needs space. Okay, so this is the paradigm, and this paradigm has been extended to other inequalities, not just the Sobolev inequality, other inequalities, for example, from harmonic analysis, especially to Strickard's, Stein-Thomas, and spectral cluster. So I will talk a little bit about Stein-Thomas, but not that much about Strickard. I'll talk about these two. And this program was probably initiated in 2014 by Frank Levin, Lieb, and Zeiringer. So they did something for streetcars, and then Frank and Saban, they considered this Stein-Thomas and other inequalities in 2017, and since then this has kind of a lot of people have proved various inequalities for classical inequalities in harmonic analysis and for n functions. Okay, what are the applications? Why is this useful? Well, okay, so these streetcar inequalities, for example, they are useful in PD, for example, the Hartree equation. So PDs, for many-body that come from many-body quantum mechanics, and stability of matter is something that the original leap theory inequality was actually tailor-made for. And I will also mention some connections to the Fourier restriction problem and Kekeya problem. I kind of singled out the application to spectral theory because this is a spectral theory conference. So let me just so here this is the leap theory inequality, but in a dual form. So in the previous slide, I put the inequality for n orthonormal functions. You can dualize these inequalities, and then you get inequalities for eigenvalues of a Schrödinger operator. That's actually this is how Lieb and Thiering first proved this inequality, and then later people developed techniques to prove this inequality on the previous slide directly. But for spectral theory, this is actually what may be more interesting. And I just want to highlight that the Lieb Thiering inequality in this form can be seen as a non-asymptotic version of the Weil law. So basically here the h bar doesn't play any role. This inequality is scale invariant, so prove it for h equal to 1, then you have it for any h, but this is not asymptotic, right? This is an inequality that's true for any h. And what is also maybe interesting is that, so you can prove the Weil law using semi-classical tools. I mean, for that remainder term, you can do some very primitive proofs, but a priori this little o, this depends on v, so you might decide that you want to prove this for smooth functions, v, or continuous functions, but then, oops. So once you can prove the asymptotics for smooth functions and you know the Lieb Thiering inequality, you can use the Lieb Thiering inequality to get the asymptotics for the class of functions for which the main term makes sense. So this is another application to spectral asymptotics of this type of inequalities. And I will talk a little bit about Lieb Thiering inequalities for complex potentials, but this is not the main focus of the talk. But they are kind of consequences of these spectral cluster bounds from harmonic analysis. So now let me give you kind of an abstract picture here. So what is the idea? So in a very abstract setting, we start with a Hilbert space separable, let's say complex, and some measure space, and we know that some operator is bounded from h to LQ for some q bigger than 2. And then if we do the naive thing, so if we just assume that, let's say all the functions are normalized in h, and then we look at this expression here. So some people call this a square function. Mathematical physicists would write this without the square root and then call it a density. Okay, I will try to avoid terminology from physics, so let me just call it a square function. And so if you just do triangle inequality, you get the norm of t times the square root of the number of functions. And again, this is sharp if all the fj are the same. If you assume orthogonality, then the question is, can we do better? So can we replace this square root of n by some smaller power? And I like to write the power like this. So n to the 1 over 2 alpha, where alpha is bigger than 1. So this is a power of n that is smaller than 1/2. And in general, it turns out that you can always do this if you're interested in L infinity, and you don't need much information about the operator t. But for q less than infinity, then there is no general result of this sort, and in general it's actually false. But if your T is sufficiently nice, like if it's one of these comes from problems in harmonic analysis, say, that we're going to discuss, then you can do something. Okay, I just put the proof. You can see the proof for q equal to infinity is really extremely simple. So what you do is you assume. Let's assume that this h is just the same, L2 of x, and let's assume that the kernel of t, the Schwarz kernel of t, is continuous. So we can write things like kxy pointwise, right? And then I just fix x and define a function of y in this manner, and then I can write the action of t on the function fj at the point x as an inner product with this kernel kx, right? And then you just sum, you square, you sum, and then use Bessel's inequality. So Bessel's inequality is what gives you what is really at work here. So you see Bessel's inequality just is used here. It tells you that this is the L2 norm squared of this kx. Take the sup over all x, and then you just recognize that this expression here is exactly the square of the L2 to L infinity norm. That's the proof. So for L infinity, you don't get any power of n. It's as good as you can hope for. So here's a counterexample for smaller q. I mean, I don't really put the counterexample. I just say like what the idea is. And this has been communicated to me by Carberry and Hanninen. So assume that T is an approximate isometry, so that for all functions you have this, upper and lower bounds, and then you can actually not do better than this square root of n. And if you look at this condition, then clearly an operator satisfying this cannot be compact. So the enemy here is kind of the lack of compactness of this operator T. And the T that are nice T that we will study, they have some good compactness properties and some quantitative and local sets. And then I also want to point out the similarity of these types of inequalities to the Marcinkiewicz segment inequality. So Marcinkiewicz segment is an inequality, basically tells you that if you know an operator is LQ bounded for any q between 1 and infinity, and for a fixed q between 1 and infinity, then it's also LQ bounded as a vector valued operator. So this is just this inequality, and it's proved by using Rademacher functions. And the proof of this counterexample also uses this kind of randomization argument. Okay, so here I want to say that what we actually do to prove an inequality like this is via duality, just as Lieb and Thirring proved the Lieb-Thirring inequality by proving an inequality for the negative eigenvalues of a Schrödinger operator. So, and the dual inequality to that one is this inequality here. So this is not an inequality for function, this is an inequality of operators. So what you have on the left is you have a Schatten norm or a weak Schatten norm. So the weak Schatten norm is recalled here, I will comment on it. And then you just have some dual norm of this W. So the Q is basically, this comes from dualizing this LQ norm here. And maybe I should write, there's kind of one intermediate step that you need to go from here to here. Namely, you can write this inequality above, the first one. You can write it using operator notation, and this comes from many-body quantum physics. So you put this these fj's into a density. So this is an operator. This is my notation. This is physics notation for the rank 1 projector onto this.
Hard to read.
Because of the. So this is just a projection onto the span of fj, and then
It's a tensor product or a Ket1?
Yeah, Kepler.
Oh,
Okay, it's it's a rank 1 operator.
it was not clear if it's an X or two triangles.
Yeah. This is yeah, okay.
Thank you.
Okay, and you look at the density associated to this row gamma. So the density is just so row of X. This is just the kernel on the diagonal of this gamma. And then this inequality there would read like this. So you take rho of T gamma T star, take the square root, say, to match the notation, LQ X, and bounded by C times, and then this n to the 1 over 2 alpha is exactly the Schatten norm of this gamma in S alpha. And then once you have this, you can dualize. You can write this LQ norm as a sub over this function times a W squared integral, and then you arrive at this inequality there. And this is what we use almost all the time. So just like in the Lieb-Turing case, there is at the moment there is no good way to prove these inequalities directly. In the Lieb-Turing case, after a long time, people have figured out how to prove them directly, but we are not at this point. So we use these dual inequalities. Okay, and just let me recall what I mean by these Schatten norms. So my definition of the weak Schatten norm here, so, SP infinity, is this expression here, and note that this is equivalent norm to this more standard expression, but this expression here is only a quasi-norm, so it doesn't satisfy the triangle inequality, and this one here is actually a norm. And this is quite convenient for us to use, that it satisfies the triangle inequality. And the standard Schatten norm, just to recall, is this is just the little LP norm of the singular values of K. Singular values of a compact operator are just the eigenvalues of the square root of K star K. Okay. What happened? Okay. I just want to say that you can prove this inequality with coefficients 1, or you can prove this inequality with variable kind of coefficients. They can be complex numbers. In physics, the new J would be between 0 and 1, but we can prove it for any sequence of complex numbers. The only difference is that if you want to prove this, then you see here you have to prove the estimate with a strong Schatten norm, not with a weak Schatten norm. So that's the only difference. Okay, so now I want to talk about the spectral cluster bounds for rough metrics. And as I mentioned, I will concentrate on two cases, the C2 case and the Lipschitz case. We also have results for everything, for CS metrics for S between 0 and 2, but really nothing interesting happens between Lipschitz and C2, and really nothing interesting happens below Lipschitz. And the reason that nothing interesting happens below Lipschitz is that there are examples of Hölder metrics where you can construct exponentially localized quasimodes. So actually you can, so this is your, so if this is our manifold, let me just draw it as a square. If you start with a Hölder metric, so S less than 1, then then there will be a scale, a smaller scale where the metric is approximated by Lipschitz metrics, and for these metrics you can prove bounds, but then basically you cannot. What happens in kind of two disjoint Lipschitz regions is completely disconnected from each other. So the only thing you can do, because you can construct quasimodes that are exponentially localized to one of those regions, is the best you can do in this case is you just sum up the individual bounds. So we'll focus on C2 and Lipschitz. Okay, so before we do that, let's recall the Fourier extension operator that was discussed in yesterday's talk. So this is you take a density on the sphere, and you Fourier transform this density. You get a function on Rn, and then the Stein-Thomas theorem, which was also mentioned in yesterday's talk, tells you that that this function lies in a certain LP space. This is the critical exponent here, and that's the best you can do. That's the best you can get. So it doesn't. I mean, you see, it's trivial to show that that the function is bounded, right? Because you're integrating over a compact set, but the function cannot be in L2, right? If G is in L2, then the Fourier transform of G is no better than an L2 function, so you cannot hope to get L2 bounds here, but this is the smallest possible exponent that you can get. And there is a version for orthonormal functions by Franck and Sabin, so which says that for any orthonormal system, Gj in L2 of the sphere, you have this this improvement in terms of, improvement in terms of the number of functions. That this is better than just taking this inequality and doing trimal inequality, right? And I will comment a little bit like on the relevance of this particular exponent. You can see that n divided by n plus 1 is kind of barely less than 1, but it's still, it gives you some non-trivial, there are some non-trivial conclusions from that that are quite surprising. Okay, so now this is kind of a interruption of the main line of the talk, so applications to spectral theory. I want to talk a little bit about these Schrödinger operators with complex potentials, and so mainly what I'm talking about is applications of this inequality here, right? The Euclidean Stein-Thomas inequality, or more generally, kind of closely related resolvent inequalities, resolvent bounds in Schatten spaces. Okay, and so let me put the semi-classical parameter h bar there. So you see, using these resolvent bounds and using some kind of standard arguments in complex analysis, well, actually one has to use some slightly non-standard version of Jensen-type inequalities due to Borishev, Golinsky, and Kupin. One can prove something that looks like a Liptirian inequality in spirit, in the sense that this is a sum of powers of eigenvalues here, that the delta each a just means the distance of each a to the positive half-axis, the essential spectrum, because in the case of complex potentials, the accumulation of eigenvalues can happen not just to 0, but also to any point in the essential spectrum. And so the exponents, they are just, the homogeneity is correct. Both sides have the same homogeneity, so this is scale invariant. But so what you can see is that it's kind of a non-local inequality, especially if alpha divided by gamma is bigger than 1, which is the case in all the applications that we have. So this is non-local in the sense that, Liptirian inequality for real potentials bounds a sum by an integral, or a trace by an integral, and this bounds a sum by a power of an integral. So in the standard Liptirian inequality, each piece of the potential kind of contributes additively the same way, but here this is kind of non-local because the power is bigger than 1. And this is not completely understood, but this is the topic of a different talk. So, but I just want to point out that what one uses to prove these bounds is are these uniform resolvent inequalities in Schatten spaces. Okay, and here's something completely different. This is an application to harmonic analysis. So Lieben-Thiering meet Kakeya, and this is just this is an unpublished observation, but I thought it's kind of an interesting one, so I wanted to include it. What is a Kakeya set? That's a compact set that contains a unit line segment in every direction, And as probably most of you know that recently the Kekaya conjecture, so Kekaya conjecture says that every Kekaya set in Rn has Hausdorff dimension n, and recently this was proved for n equal to 3. And it's been known for n equal to 2 for a long time. So we cannot compete with these kind of results. But so there is a connection to these orthonormal function bounds. So namely the orthonormal Stein-Thomas inequality. So if you take as your orthonormal functions, so you are on L2 of the sphere, and then you take spherical caps of the sphere. And so these spherical caps, they are disjoint, so the GJ have disjoint support, so they're certainly orthonormal. I mean, if you normalize them, they're certainly orthogonal. And then the standard calculation in Fourier analysis tells you that if you take the Fourier transform of such a cap, so this is a cap which, so the sphere has radius lambda, and the cap has diameter square root of lambda, and the direction of the cap is like this, and then the Fourier transform of, say, a bump function on this cap will be roughly the characteristic function of a long thin tube with dual, so dimensions will be 1 here, and this would be a square root of 1. And so, so in the Kekaya problem, what you usually do is you replace lines by delta tubes. So you thicken the lines a little bit. So this is this is 1 over square root of lambda. So that would be our delta. And then if you apply this inequality, what you can prove is this kind of Kekaya maximal inequality. And if you crank the wheels, there's a mechanism to go from these inequalities to dimension estimates. If you crank the wheels, then you can see that this implies that Kekaya sets in Rn have Hausdorff dimension at least n plus 1 over 2, which is not a spectacular result. But if you prove this without using this inequality, then you have to takes you 2 pages. Maybe it's kind of a combinatorial argument, but it just falls out of the inequality. If you know the inequality, and you know that Fourier transform of these functions are roughly constant on these tubes, then that's it. You're done. So it would be interesting to know whether there are more connection between these 2 topics. But
the report the other way around. If you know the combinatorial, the 2-page combinatorial of these tubes, can you reach out a conclusion about this?
That's a good question. We don't know. We don't know. But this is something we are trying at the moment to kind of see the connections between these two topics. Yes. Okay. So now I want to go to spectral cluster estimates, and so if I take the Euclidean Laplace, I can think of this Stein-Thomas bound as a bound for a spectral projection of the Euclidean Laplace, and just as it was explained in Xiaoji's talk yesterday. So I can kind of first of all I can scale this inequality. It's a scale invariant inequality, and I can average over dilation. So the inequality holds true for every point between lambda and lambda plus 1, and then I can integrate over this interval, and I get an inequality of this sort. So this is a spectral cluster bound for the Euclidean Laplacian. And of course, for the Euclidean Laplacian, as we saw yesterday, we could make this interval as small as we please. But on a compact manifold, we have to stick to 1. Right? The reason is that spectral window of length 1 kind of corresponds to knowing the wave propagator up to time 1 on the compact manifold. So this is, in general, this is the best we can do, unless we have some assumptions on the dynamics or on the geometry, but I don't want to impose any of those in my talk. Okay, so Sock proved this bound on compact manifolds for n equal to 1, so just for 1 function. And that's from the 80s, so we also heard that in yesterday's talk. And we also know what the extremizers of this inequality look like in different regimes. So here I'm just showing you the inequality at the critical exponent, but yesterday you saw that there are two regimes. One, if you're above or below the critical exponent. If you're above the critical exponent, then the extremizers will be eigenfunctions that concentrate on a point, and if you're below or at the critical exponent, then eigenfunctions or quasimodes will be localized to geodesics, neighborhood of a geodesic. Okay, and so in 2017, Franck Sabin proved this for the orthonormal function case, and what we did with, I should say, the one function bound has been generalized by Smith in the early 2000s. So Smith developed kind of wave packet techniques, parametrices for C2 metrics, and he first proved certain Strickard's estimates, and then also showed this sock bound is true for, you don't need smooth metric, you just need C2. And somehow the reason that C2 is enough is kind of clear, because if the metric is C2, then the Hamilton vector field is Lipschitz. You actually just need C11. Then the Hamilton vector field is Lipschitz, and then you have a Bell-Post flow. This is all you need to construct this wave packet parametrics. So this wave packet parametrics is a very rough parametric, so it gives you a large error. But for the sake of proving LP bounds, you can kind of, you can absorb this error as a driving term on the right-hand side and do estimate it away. Okay, and so what we did recently with Ni and with Xiaoyan was that we proved this result also for orthonormal functions. And I should say the proof is quite different to this proof of Franck and Sabin. Franck and Sabin used the kind of classical Carleston-Jolin method to prove this. So they proved LP bounds for oscillator integral operators, and this is kind of hard to do in the C2 case, because, so you will see later, I will discuss the proof a little bit, you have to modify things, and you have to so it's more convenient to work with certain quasimode bounds rather than with these oscillator integral operators. So, but I will discuss this a little bit. And then below C2, in the one function case, if n is equal to 1, there are always losses in lambda, and these losses are unavoidable. They're sharp. So by counterexamples of Koch-Smith-Tataru and Smith-Sock, and but the positive results, the best possible positive results, are known at least for Q below the critical exponent. What happens above the critical exponent is a bit more mysterious. So it's conjectured, for example, for Lipschitz, it's conjectured that for a certain Q above the critical exponent, you will have perfect estimates. That's very difficult to prove. Okay, let's talk a bit about optimality. So there are, so for the case of smooth metrics, one can ask two questions. So first of all, is the power of lambda optimal? And the answer is yes, because Sock proved it. Second, for a large number of functions, if we fix the optimal power of lambda, we can ask, is the power of n optimal? And one can ask this in a kind of different ways, and Franck and Sabin actually prove optimality in the strongest possible sense. So for any number of functions that is much larger than 1, but much less than lambda to the n minus 1, this is just the maximal number of, this is the lambda to the n minus 1 is just the dimension of the subspace of eigenfunctions between lambda squared and lambda plus 1 squared. So for any such n, they can cook up an optimality example to show that the inequality cannot be improved. And so I don't want to go into detail. I will show you one kind of intermediate example. So for 1, it's trivial. For maximum number of functions, it's also not difficult, because then it's just a consequence of the optimality of the Weil law. If you take all the functions in the cluster, then you know that if you integrate this, right, you will just get n of lambda. This is the counting function, n of lambda plus 1 minus n of lambda, and then along a sequence of lambda tending to infinity, you know that you have a lower bound in terms of of that. And because because of the manifold is compact, so the L1 norm is upper bounded by any other LQ norm up to a constant. So that tells you that for the maximum number of functions, this is just true by y. And then what we're interested in is kind of an interpolation between this result for n equal to 1 and then n equal to the maximum number of functions for a kind of intermediate but large number of functions. So here's an example that is related to this, what I try to illustrate here, to this Kakeya problem. So it's sometimes called Bush example. So what you do is, so now you fatten up the sphere a little bit, right? You make this an annulus of width 1, and then you take all these caps. I just draw one of them here, but imagine we take all of them, and then you look at all the weight packets corresponding to these caps, and then you will see they form a bush, right? And they kind of go through the same. They all go through the origin, right? Because you take bump functions everywhere here, so they all go through the origin, and because this square function is always positive, right? They cannot cancel. They just have to. They just have to add up at the origin, and then you can estimate how big the LQ norm is here, and that will already give you the optimal. That will already saturate the optimal bound. Okay, so apologies for this slide is a bit overloaded, but you don't actually have to look at these numbers here. This is just telling you what these exponents are, but really the only interesting thing is this critical exponent. If you can prove the critical exponent, then the other ones are trivial. 2 is trivial and infinity is not as trivial, but kind of trivial. It's a consequence of the Weil law. So once you know what happens at the critical exponent, then you get everything. And so this delta is the same as Sox delta for n equal to 1. And the alpha here is the Schatten exponent. And you can see that if q is strictly bigger than 2, then alpha is always strictly bigger than 1. So maybe here's a picture. It's better to look at pictures than at these numbers. So for n equal 2, and I put n equal 2 because when we go to manifolds with boundary, we'll restrict to n equal 2. So for n equal 2, the critical exponent is q equal to 6. And so you have this picture here for the exponent of lambda, and this is the exponent of n. That's the Schatten exponent, and you see the Schatten exponent is equal to 0 for q equal to infinity, as we already proved. And it's trivial for q equal to 2, it's just 1, no improvement. But there is at the critical exponent 6, the Schatten exponent is 3/2, which is non-trivial, bigger than 1. Okay, so a few words about the proof strategy. As I mentioned, we don't use this Carlos and Jolene machinery, but we do something like, many of you are probably familiar with the semi-classical formulation, the Koch-Tatarus-Dvorsky. So we do something similar. We prove a kind of spectral. First, we prove that these spectral cluster bounds would follow from quasi-mode bounds, and so we prove in a certain sense equivalence of all these three. Although this is not 100% true, we have to add in some elliptic estimates to make this really equivalent. But that will not. The elliptic estimates are very easy, and I will not talk about them. So these three things are more or less equivalent. And we found it convenient to use the resolvent formulation. So here, let me state the resolvent formulation. So see, here's a resolvent of the Laplace-Beltrami. Let's take Z to be this number here, lambda plus I squared. And then I multiply from the left by an arbitrary function in this space here. And I ask whether there is a uniform constant, of course, independent of W and lambda, such that this inequality here holds in this Schatten norm. Right? This is the dual. There's a prime here, so alpha prime is just the Hölder dual of alpha. 1 over alpha plus 1 over alpha prime is 1. So again, this follows from a duality argument, similar to first you write your Quasimode bound in this way using a density operator and then do some duality argument. You can prove this. And so the difference now with the previous formulation is that so the resolvent is not a positive operator, so there's no, it's not a TT star operator. That means that there is no formulation to which this is the dual to. There is no formulation involving n orthogonal functions here, because the resolvent is not a TT star operator. But still, we can work with these Schatten bounds. You can see that if we could prove this is a stronger bound, here it's stronger than this one, just because the resolvent satisfies nice algebraic identities, so there's a resolvent identity. So if you TT star this expression here, you'll get the product of two resolvents, and you can write this as a difference of two resolvents. So when you can prove an estimate for one resolvent, you can prove this, this estimate here. And vice versa, if you can prove this estimate here, you get this, but you have to take the imaginary part of the resolvent here. So the second one is slightly stronger than the first. And well, it would be interesting to prove the second one, because this is something that is immediately applicable to spectral theory, like in these Lipterian bounds I mentioned. But so far, I could prove this for smooth metrics using a different proof, but not for C2. So we'll stick with this. And the way the proof works, or the proof starts, there are several reductions to reduce this to a kind of semi-classical problem. And what we use, traditionally people have used, is what's called paradifferential calculus. So you smooth the metric in a frequency-dependent way, and then you kind of have to strike the right balance between you cannot smooth too much, because if you smooth too much, the errors will be too large, and if you smooth too little, then the main term will not be amenable to kind of parametrics analysis. So you have to find exactly the right scale to smooth. And so for C2 metrics, the right scale is that you truncate the coefficients of your metrics at frequencies square root of lambda. So that gives you an error which is not too big and gives you a good main term. Okay, so this is maybe a bit technical. Let me just go through this quickly. So for those who care about these things, so we put our operator in a kind of fixed frequency symbol class. So symbols are bounded, and they depend on lambda. And you could also, if you prefer, you can rescale and write it in terms of semi-classical symbol classes. So that means this S lambda lambda to sigma, it means that you gain a negative power of lambda each time you differentiate with respect to C, and you pay you pay with a positive power of lambda to the sigma each time you differentiate with respect to X, but the CK in front of it means that you actually you have some you can get some derivatives for free, you can get the first K derivatives for free, and then you start paying. And so actually for us, it's quite important that we have this additional, so the metric remembers that it was Lipschitz for K equal to 1, so we are allowed to differentiate once for free, and this, at least you get, you don't get a full symbol calculus, because if you have Lipschitz, then this will be S lambda lambda, and that's just basically a rescaling of the symbol class S11, where you don't have a calculus, but because of the C1, you basically have a first order calculus for free. And then you can do first order calculus, but for the error term, you don't know that this is a nice pseudo-differential operator, you just know it's L2 bounded. Okay, and so we can put our, we can prove these bounds not just for the Laplace-Beltrami, but actually, for take your favorite pseudo-differential operator, as long as it's principal type and has to satisfy a curvature condition. So and we also be micro-localized to some to a set with where C has size at most lambda, and we ask that on the characteristic set of P, this is principal type, and the fibers have non-vanishing Gaussian curvature. So this assumption, this is kind of typical if you want to prove LP bounds, this curvature assumption. That allows you to, when you write the parametrics and when you do stationary phase, that you get good estimates for the kernel. Okay, so this is kind of the model resolvent bound for these types of symbols. The lambda here in front just means that, you know, if you have a symbol in this C2, you just multiply it by lambda, and then it's said to be in this space. So it's a symbol of order 1. So we can always, of course, the Laplace Beltrami is of order 2, but you can kind of reduce it to something which is of order 1. You pick your favorite direction of oscillation, and then you can factorize it, and you factorize away some trivial elliptic part, and then you work with this order 1 symbol. And then what you really want to prove is some kind of micro-localized resolvent bound here. So this looks very similar to the bounds in the papers of Koch and Tataru. If you replace this Schatten norm just by an operator norm, or Koch, Tataru, Zworsky as well. So Koch, Tataru, Zworsky used smooth symbol, semi-classical. This older paper, they used this exact symbol calculus with C2 regularity. So our contribution here is to replace basically the operator norm by this Schatten norm here. Right. And proof, as I mentioned, you kind of pick your favorite direction of oscillation, you do partition of unity, you factorize the symbol, you get rid of the elliptic part, and then crucially use this use a dispersive estimate, an L1 L infinity estimate that comes from the wave packet parametrics. And then, yeah, so there are different ways to prove the Schatten bound. So what Franck and Sabin do is they use analytic interpolation. So they put the operator inside an analytic family of operators, and they use the Stein interpolation theorem. We just use what's called the multilinear Hardy-Littlewood-Sobolev inequality. The reason that works is that at the critical exponent, this Schatten exponent here is an integer. So you can just write this Schatten norm as a trace, and then you can apply the multilinear Hardy-Littlewood-Sobolev inequality. Okay, now let's look at Lipschitz metrics. So for Lipschitz metrics, it turns out that these wave packets are kind of, they're too big. So these packets here, they are too big. They're not preserved under the flow. You have to look at more localized wave packets. So wave packets that have much smaller size in physical space, namely instead of 1 over square root of lambda, 1 over lambda to the 2/3 in space, and then by the uncertainty principle, they're kind of localized to scale lambda to the 2/3 in frequency. And these packets, one can show that these packets are preserved under the flow up to time lambda minus a third. So in this picture there on the left blackboard, you would basically be able to prove, if you start with the C1 metric here.
You mean when you say preserved, you mean with respect to wave evolution?
With respect to this first order, you know, I basically promoted one of my spatial variables to a time variable. So you can, so this P is a first order symbol, and the canonical model for that is something like dt plus something which
It's first order as well.
Which is first order, independent of t here, right? There's no dt, something like this. So then the flow is with respect to this. All right, okay, well, the picture is actually here. So you can prove perfect estimates on small cubes of side length lambda to minus a third, just because you have the parametrics at this scale. But then, so what you need to do is first you need to do some energy estimates to kind of propagate this to a slab, and then you sum over. So you just sum over the slabs, and when you sum over the slabs, you lose a power of landed to the 1 or 3 over Q. That's your loss. That's your estimate with loss. And this loss is sharp for subcritical. So for every Q big, less or equal than Qn, this loss is sharp. Okay. Now let me talk about manifolds with boundary. So here you have a new enemy. Remember, for manifolds without boundary, you had two enemies. You had eigenfunctions which can concentrate at points and eigenfunctions which can concentrate on geodesics. If you have a boundary, you also have eigenfunctions that can concentrate at the boundary, these so-called whispering gallery modes. So you can have, let's take the disk in R2 as an example, and you can have multiple reflections, and they will give rise to eigenfunctions or quasimodes that are highly localized near the boundary. So you see the scale of these packets that I mentioned that is exactly the scale landed to -2/3 here. And this was actually observed first in the context of LP bounds by Grieser in his PhD thesis in 1992, that SOC bounds fail on the disk. So for Q less than 8, so if you have a boundary, there is a new critical exponent. So before it was 6, now it's 8. Below 8, the SOC bounds fail, in the sense that there are losses in the exponent. And the example is very simple. I mean, you just take the Laplacian in the unit disk with Dirichlet boundary conditions. You look at eigenfunctions where n is very large, and this kind of radial momentum is very small. So you take the first 0 of the Bessel function, and then the frequency is roughly n, right? It's roughly this angular frequency, and the square normalized square of the eigenfunction concentrates in this region of the boundary and has roughly this size, and then you can calculate LP norms. You get exactly well, okay. You get a violation of SOC bounds. Okay, and then later in the 2000s, Smith and Sock proved that above 8, so below 8 you lose, but above 8 you have perfect estimates. So you see in this picture, red is the case without boundary, and blue is the case with boundary. So you have losses here. So your exponent. So here there's no. This is the delta, right? The delta Q here. This is the exponent of lambda. So here you have losses, but starting from 8 you have perfect estimates. Okay, and right. Also, I should mention that well, more than 10 years before that, it was actually proved in Grieser's PhD thesis for the case n equal 2 that if the boundary is concave, then the SOC bounds hold. So you have no loss estimates for all exponents. And Smith and Sock proved this for all dimensions in 1995. And the reason is that you kind of eliminate these multiple reflections, and you have a nice parametrics. This, maybe some of you know this Melrose-Taylor parametrics. This allows you to prove this bound. Okay, so again, don't look too much at these exponents here. Let me just explain. So for manifolds with boundary, now we have to fix a dimension to be 2. We can do higher dimensions than 2, but then our bounds are not sharp. So in 2 dimensions, they're sharp for the same reasons that the Smith-Sock bounds were only sharp in 2 dimensions, actually. So take a sequence of system of orthonormal functions in L2, and any coefficients, possibly complex, and then just look at the final bound here. So this is the bound at the new critical exponent. The critical exponent is 8 now, and we prove not quite an L8 bound, but a weak L8 bound, right? L8 comma infinity is the weak L8 bound. We don't know if the strong norm is, if the strong bound is true. We cannot prove the strong bound. The counterexamples that we have, they don't rule out the strong bound. But for purposes of interpolation, a weak bound is as good as a strong bound, right? So we use a version of the Marcinkiewicz interpolation theorem for Schatten spaces, which kind of, so away from 8 we get optimal bounds, and at 8 we get a weak bound. So here's the picture. So here's the weak bound, this hollow circle, and then here we have strong bounds. And maybe what is a bit funny in this picture is that, so if you look at the right picture, so the red line is the curve for manifolds without boundaries, so what Franck and Sabin proved. And you can see here, you know, bigger alpha are better. So the blue line is better than the red line because I'm plotting 1 over alpha. So somehow R bound seems to be better than what you get for manifolds without boundary. But on the other hand, you see that the exponent of lambda is worse. But you know, you can compensate. If you know, if you have the bound for manifolds without boundary, you can artificially increase the power of lambda and make the Schatten exponent smaller because the dimension of the subspace is bounded in powers of lambda. So dimension of the subspace is at most lambda to the n minus 1. So you can always go from a smaller Schatten norm to a larger Schatten norm by paying a power of lambda. There's no contradiction. This is a result about sharpness, so we can take any number of functions intermediate between 1 and the maximum number of functions, so n is 2 here, so it's just lambda. So, and then we can cook up counterexamples that satisfy that saturate the LQ bounds in both regimes. And they're different counterexamples. This one here for large Q, this is just the same as for manifolds without boundary. This has nothing to do with the boundary. Take an eigenfunction that concentrates in the interior of the manifold at the point. And this one is the one with boundary, where you have boundary concentration. So in the last 3 minutes, I'd like to explain this example a little bit. And this is so we have a proper proof. We actually prove it for the disk. But here I will do some hand-waving argument and basically reduce the Laplacian on the disk to some model operator called the Friedlander model. So this, I believe, is the same Friedlander as in Jared's talk. So this is basically the simplest model for a concave boundary. And if you take the Dirichlet Laplacian just by changing the boundary normal coordinates and doing a Taylor expansion here, you arrive at this model. And okay, so let's glance over some technicalities here. So this is not really on a compact manifold. I'm taking this to be the half line, but you could always truncate to an interval. And here you should also put a boundary condition at 0. So this is a bit a hand-waving argument, but it will give us the right intuition. So you can write down explicitly the eigenfunctions and eigenvalues of this operator. We just have to solve basically the eigenvalue equation of a 1D Schrödinger operator. It's just the area equation. So these are just area functions. And then but we don't use any facts about area functions. Now we just use Weil's law. So you want to fix the number of functions to be n, okay? And then if you do the calculation, if you do Weil's law, so here you put a question mark, how many j should you take? You do this computation, and then you see if you take this many j's, then you get exactly n functions. That's just by evaluating the asymptotics in Weil's law. So we know how many j's we should take. And then, so this was Weil's law for the one-dimensional operator. And now we use Weil's law for the two-dimensional operator. But we use the pointwise version. So we look at the density, the square sum of all these eigenfunctions, where we take all these j's, such that each j is bounded by n to the 2/3, and we plug this into the asymptotic formula in the pointwise Weil law. And this is just a calculation. You can calculate that this is bounded from below by this characteristic function here times this is the magnitude of the function. And you just plug this into the LQ bound, right? This is just the size times the volume here. And because our n was chosen in such a way that it's much bigger than 1 and much less than lambda, if I go back to the previous slide, you can see that the energy here, lambda squared, is basically eta squared. Because this one is, Ej is less than n to the 2/3, n is much less than lambda, so that's much less than eta squared. So it's basically the eta squared. So you get optimality for subcritical q less or equal than 8. Okay, I only have 9 seconds, so I think I will skip the proof. Thank you very much for your attention.
Okay, for the talk. Any questions?
Yeah, I got a question. It's more about subs bound for manifold boundary. So it also applies to the bounds, I guess. So when you have the boundary and the exponent is a bit worse, is it true that if you take a compact set away from the boundary, you recover subs bound for?
Yeah. These are local bounds. If you localize away from the boundary, you have the same bounds.
Can you say something about like, scale if you like take a set which is at the distance lambda to some power of the boundary?
That I don't know. That I don't know. If it's lambda dependent, I'm not sure. If it's a uniform distance away from the boundary, it's trivial. I mean, we had, you see, in the whispering gallery mode example, the scale is lambda to the minus 2/3. So I suppose if you're inside of this, if you're away from this boundary layer, then maybe you can prove better bounds. If you can rule out these whispering gallery modes. Yeah. We haven't tried.
Did you say that this example somehow is the worst?
It's the worst, yes.
Yeah. But in
This
2
has-
dimensions for 2 dimensions.
Right.
How about higher dimensions?
Yes, that's a good question. So in higher dimensions, you can do the same example. You basically just take products of this, and you can cook up a conjecture of what the optimal exponent for manifolds with boundary should be. But I think this is still not proved even for one function. This is a difficult question.
In view of the talk of yesterday, you expect that negative curvature surfaces can get also log bound. Guide me.
Not with these techniques. These techniques are very rough. So basically, I skipped the proof, but what I was going to say is that we just, basically the first step in the proof is just to eliminate the boundary, just double the manifold. And then you basically you only see one reflection. So I suppose you would have much more precise information on the multiple reflections.
My question was already relevant for manifolds without boundary. Situations where you don't have boundaries, but
if you have negative curvature.
yes.
I think that was in yesterday's talk.
Also,
Yeah.
Did you include already clusters?
You can get logarithmic improvements.
Okay. No more question? So let's thank Jean-Claude again.